Okay, so welcome to the 7th video on the discrete structure series, and we'll be continuing this video from our discussion of functions from our last video. We'll be looking at functions for computer science, and these are functions useful in various fields of computer science like algorithms and more. And then we'll talk a little bit about graphs of functions. So getting into the functions for computer science, as a part of our course, we'll be looking into 4 specific functions. And the first one is the set characteristic function. And this is something that we looked at in our last video, and this comes from that alternative notation for sets that we have based on binary strings. To recall on it a little bit, so let's say we have a universal set containing the numbers from 1 to 5, and I want to represent some set that contains 2, 3. And the idea was that we would store this in some ordered way in memory, and we would write an equivalent notation for A that contained the same number of elements as in the universal set. And the rule was for each element, if it belonged, we would put a 1, and if it didn't belong, we'll put a 0. So for example, 1 does not belong in this set, we put a 0 corresponding to it. 2 does belong here, we put a 1 here. 3 does belong, 1. And these 2 elements would be 0. So if these elements were represented continuously in memory locations, this Boolean array would represent this set. And the set characteristic function is the function that maps each element of this universal set to its output. So its input space is the universal set, and the output space is just a set containing 2 numbers, 0 and 1. And to formalize this a little bit, the set characteristic function takes any element in the universal set, u of I, and then it returns either a 1 if the universal set element belongs in the set that I'm concerned in, A, 0 in other cases. And this would be the definition for the set characteristic function. It's actually the characteristic function, so let me omit this. And to look at the behavior of this function by plugging in some inputs, I could observe that, let's say, the function when plugged in with, let's say, a 1, in our case, in this specific case, would be producing a 0, right? And the function on some input like 3 would be producing a 1 because 3 exists in A. But if I choose something that is not in the universal set, like f of, let's say, 7, and 7 is not even in the universal set, right? So this is really undefined. Okay, so the next thing that we're going to look at is the family of modulo functions. So the family of modulo functions, and these are also called the remainder functions. And this asks a very basic question: what remainder do I get when I'm dividing a number by some other number? So really, that's simple. So let's say I'm taking a number 25 and I'm dividing it by 3. What is the remainder that I get when I do this? So I could think in my head 3 times 8 is 24, so 8 full times, right? And the remainder is 1, right? So 1 would be the remainder in this case. And what did I actually do there to get to this 1? I actually took my 25 and then I took a 3 and then I wanted to multiply this 3 with something as big number as I could and then find whatever the remainder was. One number would go here and one number would go here. And the largest number that I can put in here is an 8. Because 3 times 8 is 24, and that is the largest number that doesn't exceed 25. And doing that would leave me a remainder of 1. And the way I write this is by saying that 25 is congruent to 1 modulo 3. So when I'm dividing by 3, the remainder is 1. And you'd see that 4 is also congruent to 1 modulo 3, right? So any multiple of 3 and 1 above that is going to be, 1 modulo 3. So to formalize the same concept, if I'm dividing any given z with any n, what I want to do is to be able to write something like this. I want to be able to write z equals some k times n plus my remainder. And for given z and n, if I'm able to write this kind of equation, I could conclude that z is congruent to r modulo n, right? So this is just a formal definition using only variables. And when you are formally defining this, it's important to make one note. The value of r should obviously be, at least 0 or more than that, but it should definitely be less than n, whatever my modulo factor is. Otherwise, it's not the remainder, is it? I could divide it one more time, so to speak. And before we move on to the next topic, let's look at the nature of this modulo function. Is this function really 1 to 1? And is it onto? And the way we think about 1 to 1 is, can 2 inputs produce the same output, right? So that's always the question that we ask. And in this case, the answer is obviously no, right? Because 25 is producing an output of 1 and so is 4. So 25 is also congruent to 1 and 4 is also congruent to 1. So if you think of the input space containing 4 and 25 somewhere with other numbers, both of these are mapping against 1. So the function is not 1 to 1. And is this function onto? Is everything in the output space covered? I'll let you guys to think about that. Okay, so the next two functions that we're going to look at are going to be floor and ceiling functions. So floor function and the ceiling function. The ceiling function. So these are functions that calculate the whole numbers below or above a given number. So what do I mean by that? The floor function of any number x is denoted by putting a floor below it, like so. And it is defined as the biggest integer that is less than x. So it just pushes the number back to the floor, whatever the floor integer is. For example, 3.5, when we take a floor of this value, we get a 3. And for 3 point, anything that is could be 0 and less than 1, the floor is going to be 3. And we define the ceiling function just in the opposite way. The ceiling function of x is denoted also by putting a ceiling above it and is defined as the smallest integer that is greater than x. And so the ceiling of 3.5 would be 4. And in general, the ceiling of any fraction that is 0 or less than 1, including 0, is going to jump up by 1. So it's going to be 4. Okay, so why are these functions useful? Let's say I'm a manufacturer and I sell 5 kilogram bags of some product. And I have 43 kilograms of material available. 43 kilograms. So how many bags could I really prepare out of the material that I have? I would start by dividing this 43 by 5, and that would give me an 8.6. But I cannot really create 8.6 bags, can I? I don't have enough for 9. So what I'm forced to do is to take a floor of this value and round it down to a 8. On the other hand, let's say I have 10 students and I want to distribute pencils among them. And pencils come in packet of 3, for example. So how many packets would I need to buy to fulfill this requirement? So I again begin by dividing. So 10 by 3, and that's 3.3 recurring. But the idea is the same. The shopkeeper isn't willing to sell me 3.3 recurring packets of pencil, right? He asks me to either buy 3 or 4. 3 is not enough for me. Therefore, I round this value up using my ceiling function and then get a 4. So these are just a few typical examples, and these functions are applicable in multitude of cases. Let's be focused on our syllabus and do a couple of problems related to floor and ceiling functions. The first question asks me to prove that the floor of twice a given value is equal to the floor of the value plus whatever the floor of the value plus a half is. And it's difficult to see something like this is true at first glance, but let's brace ourselves and prepare a few ideas before diving into this problem. So I want to highlight something relevant here. I'm multiplying this number with a 2. And you'll understand what I'm getting at. Let me look at a very specific number, in this case 0.5. What significance does it have? When I multiply this number by 2, I get a 1. And that is a whole number. If the result were anything less than 1, taking the floor of that value would drop it down to 0. But since it is a 1, taking the floor or a ceiling doesn't change it. And maybe I didn't mention this before, but you should know that the floor and a ceiling of a whole number is the same number. If I take a floor of 1, it's just 1. If I take a ceiling of 2, it's just 2. It's not like when you take a ceiling of 2, you have to jump to a 3. No, if it's a whole number, it stays there. And so getting back here, if I have any number between 0, it could be 0, and that number is less than 0.5. So it could not be 0.5. So if I say my number is x, it should be something like this, right? So in this case, the floor doesn't jump because I don't get a 1. But in the range 0.5, and it would be equal to 0.5, in this range, the floor will jump up, right? Because when I multiply this number by 2, I get at least a 1. And another little idea before we actually jump into this problem, we are able to express any real number as integer and fraction. So we are able to say 3.7 is something like 3 plus 0.7. This is true for any real number. And if I have any number x, I could write x as n plus delta, where n is the nearest whole number less than x. So the nearest whole number less than x. And delta is just a fractional part. And you'd notice that this delta, since it is a fraction, would always be between 0 and 1. It can never be 1, right? It could be 0, but not 1. So the fractional part delta is going to be in this range. Okay, so we understand these things. Now go back into this problem. So there's a pattern to this. We always want to express an x in this format so that whenever we take the floor or ceiling of n, it's just n, right? It doesn't change the value because it's already a whole number. So if we assume, and we established here that we can do that, x is equal to some whole number n plus the fractional part delta, then I could effectively rewrite this as the floor of 2n plus 2 delta, I just distributed 2, equals to the floor of n plus delta plus the floor of n plus delta plus a half. Okay, and of course you'd have to mention in your exam that this delta is between 0 and 1, and n is a whole number, of course. So this is my full range of delta, and I want to split this into two ranges. I want to split this into a range 0 less than or equal to delta less than a half, and look what happens. And then I want to look at what happens when half is less than delta less than 1, and in this case it could be actually equal to the half. So how do I know to look at these two things in particular? Because of the fact that I have a 2 as a multiplier here, right? And we established that whenever the number is less than a half, the floor doesn't jump, and it does on the other way around. So I just want to simplify this equation in context of this assumption. So what happens to this equation? So since delta is less than 1 by 2, 2 times delta is always less than 1, right? Because if delta was exactly 1 by 2, it would have been 1. So in this case, in the left-hand side, 2 times delta will not be able to change the floor because it will not be able to be more than a 1. This 2n is already a whole number, and this is something less than 1, right? So the floor of this entire thing is just going to be the floor of 2n. And that's even easier to see here. Since delta is between 0 and 1, there's no way the floor could jump above of n. So it would just be n. But since this is less than 1 by 2, I can ensure this is less than n plus 1, and the floor would still remain on n. So this would just be the floor of n, right? And here's also my floor. But again, these are whole numbers, so I can now remove the floor and see 2n is equals to n plus n. This is equal to 2n, which leads me to an identity, right? So if my delta is between these values, at least I can tell, okay, this expression is true. What about the other range? Is it also true for this range? And if it is, my proof is complete. So looking into this expression here, since my delta is now more than a half, 2 times delta will be at least 1. So in this case, the floor would jump. The floor would be the floor of 2n plus 1. The idea is 2 times delta for a value more than half would add a 1. And then this would be equal to what happens in this case. In this case, the value of delta is still not 1, right? So the floor cannot jump. It only jumped here because it was multiplied by 2. In this case, it would still remain n. And what happens here? Well, here it will jump as well because we are adding half to a value that is at least a half, right? And in this case, the floor will also jump by 1. So I'll get a floor of n plus 1. And then I write 2n plus 1 equals n plus 1 because of course n is a whole number now, and this leads to me an identity again. 2n plus 1 equals 2n plus 1, right? So whatever the range of delta I choose, I see that this holds as an identity, right? And this completes my proof. So there's one more question. Prove or disprove that the ceiling of x plus y is equal to the ceiling of x plus the ceiling of y. And if you think about this in some depth, you realize that whenever you choose x and y such that their fractions add up to 1, something happens. Let's say x is 1.3 and y is 2.7, for example, right? And I'm choosing these values. 1 and 2 didn't really matter, the integer part, but I'm choosing my fractional part so that they add up to a 1. Now if I take a ceiling of these values, this will give me a 2 and this will give me a 3. So there's one jump here and one jump here, and then we add it to get a 5. But now if I add them first, I get a 4.0, right? And if I take a ceiling of this value, it doesn't get to jump anymore because it's already a whole number. So this counter example and so many others, right? I could choose x equals a half and y equals a half. For example, these two fractions add up to 1, and this would also be enough to disprove that this fact is true. I could proceed in the same way. I could say x equals n1 plus some fraction delta 1 and y equals n2 plus some fraction delta 2. But then this would require for me to track both the values of delta 1 and delta 2. But I know if I have these fractions so that they add up to 1, I'm going to be able to prove that, right? So I invite you to use the assumption delta 1 plus delta 2 is equals to 1. So this is a fact that you are allowed to use, and you are allowed to use these substitutions in this equation. And hopefully that leads you to a useful contradiction. So that was about floor and ceiling functions. And before I end this video, I just want to touch on the concept of graphs of functions because it is mentioned in your course for some reason. So very basic, graph is just a visualization of a function in a plot, right? So if I have a function, let's say y equals x squared, I could see by drawing, let's say, a graph like this, where this is my origin, and I want all the inputs of the function to be represented by values in this number line. If this is 0, I want these to represent the different values of x, and I want these heights to represent what the values of y are for that given x. So if I take my x to be a 0, y would also be 0 because 0 squared is 0. 1 squared would give me a 1, 2 squared would give me a 4, 3 would give me a 9, and so on. So it would be an increasing curve, and the farther you went right, the faster it would increase because every time we are squaring bigger numbers, right? So this helps me visualize what this function would actually look like. What happens on the negative side of x? So even if x is negative, the square is still positive. This function would just be symmetric about the y-axis and go this way. Now if you were y is equals to x cubed, for example, it would look more or less the same in this side, right? Because it's just, increasing numbers, increasing even more rapidly because now we are cubing it. But on the left-hand side, it will just go down because the cube of a negative number would also be negative. So these things are not particularly relevant in our discrete structures course, but since this was mentioned in your course, I wanted to touch base. Okay, so that concludes our video. In the next video, we'll be talking about fuzzy sets and their operations. So can't wait to see you guys then. Have a good day. Bye.